Forwarding procedure principles and parameters. Apart from an initial neighbor discovery phase, routing decisions should require minimal information to be exchanged between nodes and no cooperation, to avoid imposing computational load on nodes with limited computational capacity and wasting bandwidth in exchanging control packets when bandwidth is limited. The forwarding procedure developed therefore had the key goals of simplicity and distributed decision-making. This is an obvious trade-off, as the simplest design solution would be flooding, a technique used in many sensor network opportunistically routing schemes, for example see in the references therein. The immense resource consumption of this scheme renders it completely impractical when amongst the targets of a routing protocol is for example to allow for multiple flows to exist simultaneously in the network, a goal not always necessary in event detection sensor networks. Summarily, the stochastic forwarding procedure proposed is intended as a flexible solution in routing applied in a variety of networks, where lossy areas are observed due to low link quality and that the topology is sufficiently dense to require opportunistic communication. The major issues that need to be addressed in the design of the routing scheme that encompasses a stochastic forwarding procedure are, I. Deciding which node should forward a packet, 2. When to do so, 3. How to acknowledge the reception of a packet. Candidate forwarders should be selected in order to improve the performance of the end-to-end flow. On the other hand, the number of these forwarders should be limited to those that guarantee, with a high probability, the packet's progress towards their destination, in order to avoid excess resource consumption and allow better network resources utilization. Furthermore, the forwarding time differentiation between the candidates enables the mitigation of redundant transmissions, by limiting packet collisions. Lastly, since Layer 3 broadcast packets typically do not implement link layer acknowledgements, such a scheme should be devised. The destination could generate acknowledgements upon packet reception, which would be propagated back to the source, either opportunistically or via the shortest path. This would impose significant load on the network if the acknowledgements were standalone Layer 2, or Layer 3 control packets competing with the data packets and being susceptible to lossy links, which would cause significant delay until retransmission of a lost packet. However, the option of piggybacking the acknowledgements onto data packets is limiting since it can be applied only when flows of symmetric direction exist between source and destination. Hop-by-hop acknowledgements provide robustness to the lossy links and mitigate delay, on the other hand increase the overhead. Conversely, a passive acknowledgement scheme that utilizes overhearing of other nodes' transmissions, avoids imposing additional load to the network, contrary to explicit acknowledgement packets.